For this section, I'd like to talk about the development of a full adder. To get started, let's talk about the operation that we're trying to implement. It's just regular addition. So I'm showing this with 4 bits. This scales up to n bits. We just do 4 because it's a simple case. All right, so we know how to add binary numbers together. We know that there's initially 0 carry in as we get started. So we start in the least significant bit position. 1 plus 0 is 1, carry the 0. 0 plus 1 is 2. So I'd write down the 0, carry the 1. 1 plus 0 plus 1, that's 2, carry the 1, and so forth. You get the pattern. You understand how that works. So the job of the full adder is to take care of one column. All right, so we need a circuit that does each of the columns, and then we ripple that through later to make a ripple adder. Okay, so we'll see how that works as we make some progress. Okay, so that circuit's the circuit that we're working on is the full adder to take care of these columns. All right, so the next thing we want to do is we want to design a circuit. So what makes sense to do is to come up with the truth table. So we look at all the input combinations. So what if I had a carry in? Then the sum would be a 1 with a carry out of 0 for this input combination. So that's the thing. We go through all the input combinations and fill out the rest of this table. I'm not doing them in the best order, but you get the idea. We now have the truth table. And what I want you to notice is when you look at this, basically the output is the sum of the ones that you see between A, B, and C. Okay, so on the first row, there's 0 ones, so this would be binary 0. On the second row, there's only 1, 1, so this comes out binary 1. Skipping down here, you see 2 ones in this row. All right, so that'd be 1, 0. And lastly, we have 3 ones, so that's 1, 1. So it's another way of looking at the output of a full adder. You just read it as counting. Okay, so next what I want to do is dial this back a little bit and talk about that least significant bit position. In the least significant bit position, we don't have the carry in. So we get a simpler circuit for that position, and you can call that the half adder. Okay, and so with a half adder, because you have fewer inputs, it's pretty easy to come up with that circuit by inspection. So if I look at this is the truth table for the half adder. We don't have that carry in. Okay, so I look at each of the combinations, fill out the truth table. I think it's obvious if I have, it would be obvious if I put these in the right order. Okay, so it should have been carry in the most significant bit position and S in the least significant bit position. But this is the valid truth table, even though I've got the output ordered a little strangely. And so you can look at what happens. This is the output function for exclusive OR. All right, so S is just A exclusive OR B. And this column is just AND for A and B. All right, so I think that's by inspection. All right, so now we have this circuit that's known as the half adder. Okay, so you take A and B, you exclusive OR those together to get S, and then you AND those together to get C. All right, so pretty simple circuit. Okay, so why the half adder? It's half because it doesn't have that carry in stage. All right, so next thing I want to do is compare 2 different ways of implementing the logic or the circuitry that you would need for a full adder. The first way is we're just going to do the Carnot map minimization of C out and S. All right, so here's the truth. You take the truth table and you make a Carnot map. This is what you get for the full adder. So the minimization is you circle these 3 groups. We've done this before. This is the output. All right. From here, you could calculate the number of transistors that you would need to implement this. We're going to do that a little bit later and compare implementations. Okay, next you would need the sum bit. And if you do the Carnot map for the sum bit, you get this checkerboard pattern. And it turns out a checkerboard pattern like this tells you, oh, this is going to be exclusive OR. All right, so if you read all these product terms, this is what you'd get. And then we have a definition of exclusive OR as a primitive. this would be a 3-input exclusive OR function shown here, where you just take A, exclusive OR B, and then exclusive OR that with C. Okay, so there we go. We've got the circuitry that we would need for a full adder using 2-level minimization. Okay, it turns out there's another way to do it. All right, you could take this and you could do the transistor count and see what you get, in terms of how big the circuitry is. Another thing you could do is you could notice, people have noticed this in the past, that you can build a full adder out of 2 half adders, and it turns out you get less circuitry. All right, so what I've done here in this graphic is you can trace through all the combinations here. Like if I have zero ones here, the output is 0, 1. I'm sorry, 0, 0. There's no ones, all right? If carry in is a 1, then what I know is, I have 1, 1, so 0, 1 is binary 1. That works. If I have B equal 1 and Cn equal 1, 1, 0, that's 2, all right? So you can go through here and verify all the elements of the truth table for a full adder and prove to yourself that this actually works. Another thing you could do is you could actually trace through the wires here and come up with the logic function. Okay, so you can trace through C out and find that it's A ended with B, so you get this stage here, A ended with B, all right? And then you have A exclusive OR, okay, A exclusive OR ended with C in, and that's the answer for C out. From there, you could do some Boolean algebra and prove that this actually matches what we had from the minimization that we had before. Okay, so it matches the K-map. All right, I have to say it's not obvious going from this step to this step. You would take some Boolean algebra to get there. My point is, we have 2 different circuits that implement the same truth table. All right, so why do we care about that? Well, we could compare these. And it turns out that if you look at the 2-level SOP, all-NAND, all right, the first one that we did with the Carnot maps, that takes 56 transistors, but the delay path through that circuit is only 3. All right, so with the 2 half adder configuration, we get significantly fewer transistors, 36 transistors, so less area on an integrated circuit, less power consumption, all those things would be good. But we're giving up a little bit of the speed because the critical path through that particular circuit is up to 6 transition times. All right, so I wanted to show you this because it shows you the different trade-offs that you have when you start implementing circuits in different ways. All right, so in some cases, if you wanted a smaller circuitry and you don't care about how fast it goes, you could go with the 2 half adder approach. And I think that has some historical significance to it because in the beginning, we were more worried about transistor counts than we were speed. These days, that's a different discussion. Okay, so the next step here is let me first say, neither one wins. It depends on what you want. Okay, so if you were going to compare these two and try to come up with a winner, this one wins on critical path, but it loses on transistor count. This one loses on critical path, but wins on transistor count. So it depends on what your goal is. All right, so let's pull all this together. How would we use all this? Well, we could make ourselves an adder now because we know how to handle each of the columns. So for the first least significant bit, we don't have a carry in, so we could use a half adder. And then we could propagate that and go to take the carry out of the half adder, put it to the input of the next full adder to get that column taken care of. And you can see, you cascade this together and you have yourself an adder. All right, so you can flip the bits here and see what happens with the different situations. So like I'm going to flip this bit and you see the carry out lights up and it goes to the next stage, which forces that to carry out. The carries as you play with this, that's what you should do. Play around with this and make sure that you understand that it takes steps for this carry to propagate through to the output. You have to start over here at the right and move your way to the left. And if you had, a 16-bit adder or a 64-bit adder, this would take significantly longer because there's a lot more to that ripple process. Okay. Okay, so you can check answers here and click on different combinations and make sure that you understand how a ripple 4-bit carry adder works. Okay, so the cost of the rippling, each column can't settle till the previous column settles out. I think you play around with this, it becomes obvious. Okay, before we move off of this, I don't want to leave you with the impression that the answer is either a 2-level minimization or an implementation with 2 half adders. It turns out the full adder is a primitive element on a lot of chips because we want to do computations, we want to do those efficiently. If you had, for example, a multiplier on a chip, a 32 by 32-bit multiplier contains roughly 1,000 full adders. And so you want to make the full adder the best it can be. And so what that implies when you take a VLSI course, what that implies is you're going to get away from thinking of building up full adders out of gates. You're going to look at just how do we make a transistor circuit that directly and efficiently computes the full adder. All right, so there's been a lot of research on that. This is beyond the scope of this course, but the point is you have different methods. You use smaller transistors, have different delay times. I just wanted to make sure that you understand that trade-off. So I wouldn't worry about these details. The main thing is it's beyond the scope of this course, but we care a lot about implementing something that's going to be used a lot for a lot of calculations. We want to do that efficiently. Okay, so that wraps up the discussion of the full adder and how it's used in a ripple adder. We'll go on to talk about, how could we come up with something that's a little faster than a ripple adder? And then also, by the way, how can we come up with something that does both addition and subtraction? Okay, so we'll be talking about those 2 topics.